For the first question regarding the minimum demand on the service for 300 duplex receptacles in a hospital, the key to understanding the correct application of the National Electrical Code, or NEC, lies in the specific use and location of those receptacles. Table 220.42, the lighting load demand factor, is indeed the appropriate table to use in this scenario, specifically because the question refers to receptacles within a hospital setting, particularly patient care areas. The NEC distinguishes between different types of receptacle loads based on where they are located and what they are likely to be used for. In hospital patient care areas, receptacles are often used for lighting, medical equipment, and other patient-related devices. These are considered essential for patient care, but their usage patterns are such that not all receptacles will be heavily loaded simultaneously. This is where the demand factor comes in. A demand factor is a reduction applied to the total connected load to account for the fact that not all loads will be operating at their maximum capacity at the same time. Table 220.42 provides these demand factors specifically for lighting loads, which, in the context of hospital patient care areas, includes the receptacles used for lighting and related equipment. Table 220.44, demand factors for non-dwelling receptacle loads, on the other hand, is more applicable to general use receptacles in commercial or industrial settings where the loads are more likely to be diverse and include a higher proportion of appliances and equipment with potentially higher and more sustained demand. These receptacles are often used for things like power tools, portable machinery, and other non-lighting applications. Using Table 220.44 for hospital patient care receptacles would likely result in an overestimation of the actual demand, leading to an unnecessarily large service and higher costs. Let's break down the calculation using Table 220.42. The initial calculation involves multiplying the number of receptacles by the volt-ampere rating per receptacle. In this case, it's 300 receptacles multiplied by 180 volt amps, which equals 54,000 volt amps. This represents the total connected load of all the receptacles. Now, applying the demand factors from Table 220.42, we consider the first 50,000 volt amps at 40% demand and the remaining 4,000 volt amps at 20% demand. This is because the table recognizes that the initial portion of the load is more likely to be utilized simultaneously, while the additional load has a lower probability of being fully utilized concurrently. Thus, 50,000 volt amps at 40% yields 20,000 volt amps, and 4,000 volt amps at 20% yields 800 volt amps. Adding these two values together, we get a total demand of 20,800 volt amps, or 20.8 kilovolt amps. This is the minimum demand required for the service based on the NEC and the specific usage characteristics of hospital patient care receptacles. In summary, the selection of Table 220.42 over Table 220.44 is determined by the specific application of the receptacles. In hospital patient care areas, where receptacles are primarily used for lighting and related equipment, Table 220.42 provides a more accurate and appropriate estimate of the actual demand. This is because it takes into account the usage patterns of these receptacles, which are typically characterized by lower simultaneous usage compared to general use receptacles in other settings. For the second question regarding the number 8 RHH conductors without an outer covering that can be installed in a 1/1/2-inch electrical nonmetallic tubing, or ENT, the calculation revolves around the concept of conduit fill. Conduit fill refers to the percentage of the conduit's cross-sectional area that is occupied by conductors. The NEC sets limits on conduit fill to ensure adequate space for heat dissipation, ease of pulling conductors, and to prevent damage to the conductor's insulation. The allowable fill percentage depends on the number of conductors within the conduit. For 3 or more conductors, the maximum allowable fill is typically 40%. However, in this specific scenario of RHH conductors without an outer covering, the fill factor is specified as 53%. This higher fill factor is permitted because RHH conductors without an outer covering have a smaller overall diameter compared to conductors with an outer covering. This allows more conductors to fit within the same conduit size while still maintaining adequate heat dissipation and ease of pulling. To determine the number of conductors that can be installed, we need to know the cross-sectional area of both the conductors and the conduit. The cross-sectional area of a number 8 RHH conductor is 0.13 square inches. The cross-sectional area of a 1 and 1/2 inch ENT conduit is 1.77 square inches. Now, we can calculate the allowable area for conductors within the conduit by multiplying the conduit's cross-sectional area by the fill factor. In this case, it's 1.77 square inches multiplied by 0.53, which equals 0.9381 square inches. This is the maximum area that can be occupied by the conductors. To find the number of conductors that can fit, we divide the allowable area by the cross-sectional area of a single conductor. So 0.9381 square inches divided by 0.13 square inches equals approximately 72.16 conductors. Since we cannot install a fraction of a conductor, we round down to the nearest whole number. Therefore, the maximum number of number 8 RHH conductors without an outer covering that can be installed in a 1 and 1/2 inch ENT conduit is 72. In conclusion, when determining the number of conductors allowed in a conduit, it is crucial to consider the type of conductors, the type of conduit, and the applicable fill factor specified in the NEC. For RHH conductors without an outer covering, the higher fill factor of 53% allows for a greater number of conductors to be installed compared to conductors with an outer covering. However, it is always essential to perform the calculations carefully and adhere to the NEC guidelines to ensure a safe and compliant installation. Now let's clarify the discrepancy regarding the answer of 13 versus 14 in the original problem. The calculation performed, which was 1.77 divided by 0.13 equals 13.69, is actually not considering the fill factor correctly. While the initial instinct to round down might seem correct, the NEC provides specific guidelines for conduit fill calculations, and it's important to adhere to them precisely. Firstly, it is critical to identify the correct fill percentage for the specific type of conductor and conduit being used. In this case, RHH conductors without an outer covering have a fill factor of 53% when 3 or more conductors are installed in a conduit. Secondly, the calculation should be performed to determine the allowable area for the conductors within the conduit. This is done by multiplying the cross-sectional area of the conduit by the fill percentage. The result is the maximum area that the conductors can occupy. Thirdly, the number of conductors that can be installed is determined by dividing the allowable area by the cross-sectional area of a single conductor. The result is the maximum number of conductors that can fit within the conduit. Fourthly, the NEC specifies that when calculating conduit fill, any fraction of a conductor is disregarded. This means that if the calculation results in a value with a decimal, the decimal portion is dropped, and the whole number is taken as the maximum number of conductors allowed. Therefore, if the calculation results in 13.9, the decimal portion, 9, is dropped, and the maximum number of conductors allowed is 13. This is because installing a fraction of a conductor is not physically possible. In the specific scenario of the question, the calculation 1.77 divided by 0.13 equals 13.69 is not entirely accurate. The correct calculation should be based on the allowable area for conductors within the conduit, which is determined by multiplying the conduit's cross-sectional area by the fill percentage. Assuming a fill percentage of 40%, the allowable area would be 1.77 times 0.40 equals 0.708 square inches. Dividing this by the cross-sectional area of a single conductor, which is 0.13 square inches, we get 0.708 divided by 0.13 equals 54.46 conductors. Rounding down, the maximum number of conductors allowed is 54. However, if the fill percentage is indeed 53% as stated for RHH conductors without an outer covering, then the allowable area would be 1.77 times 0.53 equals 0.9381 square inches. Dividing this by the cross-sectional area of a single conductor, which is 0.13 square inches, we get 0.9381 381 divided by 0.13 equals 72.16 conductors. Rounding down, the maximum number of conductors allowed is 72. Therefore, based on the NEC guidelines, the answer of 13 is correct. The instinct to round down is indeed the appropriate approach when calculating conduit fill.